Okay, so I have posted on the board some homework. Chem 101 assignments 13 and 14 are already posted. 13 is review of moles and molarity. We're going to be talking about concentrations, so I want to make sure that we have that material from last semester still in our brains. And then homework 14 is going to be the new forms of concentration that we're going to be looking at in class today. So those are the things we're going to be paying attention to. And then I will post a prepare to learn for when we get back so that we all know what we're doing on that Monday and we'll be on the same page. So that kind of covers what's going on until then. They're not due until the night before you come back, so you got plenty of time to look at them and mull over them and whatnot. They're a little bit longer than the typical assignments, just because there's a lot of math involved. So have your calculator, have your periodic table. You can do this, I believe you. Any logistical questions before we get started? Okay. So we are going to be talking after spring break about colligative properties. That's in section 11.4. We'll also go back and pick up 11.3, but I'm going to focus on 11.4 first. So for the colligative properties, we need to know concentration, but the equations use different forms of concentration. So we're going to look at how we might measure concentration. All right, so I have here colligative properties is in section 11.4. Colligative properties are properties that depend only on the concentration of the solvent, and that's kind of ish, but we'll get to that at the end of the chapter. Right now, we're going to say they depend only on the concentration of the solvent. So that means that it doesn't matter whether I'm talking about sugar or salt. It doesn't matter whether I'm talking about benzoic acid or oxalic acid or ethanol. They're all going to behave the same way at their concentrations. So the four properties we'll end up looking at are vapor pressure depression, and that's going to be using something called Raoult's law. So from the name, you can tell the vapor pressure is going to go down as we have concentrated materials. Because the vapor pressure is going down and because the vapor pressure is related to the boiling point, if the vapor pressure is lower, it's going to take a lot more energy to get us to that same pressure as the surrounding environment. That's how we get to a boiling point. So that means that our boiling point is going to go up. So we have boiling point elevation. When we have foreign particles in between our particles that are trying to solidify to form crystals, that's harder to do. You got to push those particles out of the way. And so freezing point goes down, freezing point depression. And then the last one is osmotic pressure. We're not going to do calculations with that because in this level of chemistry, that's not something that comes up a whole lot. We need more to be familiar with what the concept is because that applies to biology and how to calculate. All right, so we said it depends only on the concentration of the solute, but we need to be a little bit more specific. It depends on the concentration of dissolved particles. And so we might ask ourselves, well, why are we making the distinction between dissolved particles and the solute? Doesn't all the solute dissolve? For non-electrolytes, that's going to be the same quantity. So remember, our non-electrolytes are our covalent compounds, sugar, for example. So I dissolve a certain number of molecules, that's the number of molecules that are in it. And so there's no difference in our calculation. But if I have an electrolyte, those are the things that conduct electricity, they separate into ions. And each ion acts as an individual particle because, as you recall from the beginning of the chapter, each ion is separately surrounded by the solvent. Okay? And so then we need to take into account the factor of how many ions there are. So if I look at sodium chloride, 1 molar sodium chloride, that might be how the bottle is labeled, is actually 2 molar in ions. Okay, so remember capital M is molarity, that's moles per liter, that's a way we do concentration. All right, so we would say that methanol, when it dissolves, is only going to form methanol. And it's going to have, I'm going to use an I for this factor, it's going to have a factor of 1. We change the concentration by a factor of 1, which means 1 times anything is itself, it doesn't change. Sodium chloride, when it dissolves, it's going to form its separate ions, and so we have a factor of 2. Now, if I have magnesium chloride, I need to pay attention to how many chlorines there are, because the chlorines don't buddy up together. Instead, I get 1 magnesium ion and 2 chlorine ions. So that means I have a total factor of 3. Okay, so we're looking at how many ions we form. Now, one thing that trips people up sometimes is when you're looking at polyatomic ions. So last semester, we asked you to memorize several polyatomic ions and to know their names and their formulas. And this is part of the reason why is you want to be able to recognize them. They stay together as a group. So as we were looking at nitrate and sulfate and chlorate, when we were doing dot structures, we showed bonds, covalent bonds between the central atom and the oxygens. Okay, covalent bonds, easy to break, hard to break. Hard to break. Water molecules are not going to break those bonds. So let's say I have potassium nitrate. I'm going to get 2 potassium atoms because the potassiums by themselves as one atom are an ion. And I'm going to get 1 nitrate. The nitrogen will not split up from the oxygens. Okay, so this means I again have a factor of 3. All right, so do you think you kind of have the idea of how this works? All right, I'm going to write down a few of them. You try them out, talk with people around you, see if you're coming up with the same thing. So let's do barium hydroxide, lithium phosphate, and sucrose. So ultimately, we're interested in what is this factor that will multiply the concentration by. But the way we get there is by figuring out what particles are formed. All right, Lamb, what do you think the factor is going to be for the barium hydroxide? 3. I would agree with that. So did you get that by saying we're going to get a barium and we're going to get 2 hydroxides?
Yes.
Good, very good. All right, Lauren, what did you get for the lithium phosphate? 4. Do I have agreement on that? Yeah. And this one is kind of tricky. You might have thought, oh, there's 4 of these POs, but remember that your if you have something that you're applying the number to everything, you would have it in parentheses. So the hydroxide we put in parentheses, and that meant we had 2 of the whole thing. So since there's no parentheses, the 4 only applies to the oxygen, and that's a good indicator that I have a polyatomic ion. So we don't use phosphate a whole lot. You might not have remembered that one. I could dust off that list and look it over. Okay, so we have only 1 plus. 3 lithium plus and 1 phosphate. And that has a charge of 3. All right, did anybody want to venture a guess on this last one for sucrose? 1. Yeah, so this is also a covalent compound. Okay, so before we jump right in and start counting the number of atoms that are there, we first want to consider, is it ionic? Because if it's not ionic, we don't need to worry about it. And if it is ionic, are there polyatomic ions? So in this case, we're just going to end up with the same formula back again. And I is going to be equal to 1. All right. Okay, so in a minute, we're going to be looking at acids because we also said that acids, weak acids are weak electrolytes. But first, I want to go through a couple of examples of just reviewing how to get to moles and molarity. So moles, remember, is kind of like the word dozen. It's a way of counting in groups of numbers. So it's a really big number, 6.02 times 10 to the 23rd. We never use that number for anything. We're only concerned with moles. And we find moles from the mass. In order to do that, what do I need? What other number do I need?
Atomic mass of all of
Yeah, so I'm going to need what's called the molar mass or the formula mass of the compound, which I'm going to get from the atomic masses of each of the elements. So moles is equal to mass divided by molar mass or molar weight. There's so many M's in chemistry, I do W for molar weight. And remember, we get that molar weight from the periodic table. So this is a formula. If you like to memorize formulas, I'm always in favor of using unit analysis because they can help you figure it out without having to memorize a whole bunch of formulas. So if I have 1 gram of NaCl, and I want to know how many moles, I'm going to need the molar weight. So I'm going to take my 23 for sodium, my 35.45 for the chlorine. And so that's going to give me about 58.45 grams per mole. So I'm going to have 1.0 grams. I want to get rid of grams, so that's going to go on the bottom. Go to moles. What I want goes on top, what I'm getting rid of goes on the bottom. And so I'm going to cancel these grams and have moles, and I've got this number. Where's the number going to go? Top or bottom? Bottom. So we always say grams per mole. The number sticks with whatever that first unit is. So in this case, the first unit is grams. So 58.45 grams per 1 mole. And we're going to So we get about 0.017 moles of NaCl. Right, so that's how we get to moles. Now, as I said, we're looking at concentrations, so we want to probably know how much this is in a solution. So remember, moles is an amount, so it matters how much is there, whether I have a little bit or a whole beaker full or jars and jars and jars. That is an amount. Concentration is one of those properties that is not dependent on the. So I have the same concentration, whether I have the whole bottle, the amount in my beaker, or the amount in my burette, the concentration stays the same. So molarity, we use a capital M, is equal to moles of solute divided by liters of solution. Sometimes we say V for volume. Remember that it's liters. So if I dissolve this in 250 milliliters of water, now technically I want to know what the volume of the whole solution is. It turns out that for dilute solutions, we can usually just approximate it, especially if we don't need a lot of precision on our number. So I'm just going to make the assumption that our whole solution is 250 milliliters. I will let you know if that's not a fair assumption. But in this case, we're going to say the whole solution is 250 milliliters. So we're going to have 0.1017 moles divided by, I need it in liters. So usually in chemistry, when we are converting, we move that decimal 3 places. So I'm going to have 250 milliliters, divide by milliliters. I'm going to get rid of that. I'm going to go to liters. That's going to go on top. And so milli means 1,000. So do I have 1,000 milliliters in 1 liter or 1,000 liters in 1 milliliter? Exactly. So milliliters, about the end of your pinky, or miniature marshmallows, about a milliliter. And then beverages like this, they're a little less, but they're in the ballpark of a liter. So if that helps remember which way it goes. So we're going to have 1,000 on the bottom, 1 on the top, and that's going to move my decimal place over by 3. So I'm going to have 0.250 liters. So this is going to give me 0.068 molar NaCl. So my whole formula is 0.068 mole. But if I'm interested in what's the concentration of ions, then I multiply by my factor. So for sodium chloride, we said that was a factor of 2. And that's going to give us, with rounding, 0.14 molar ions. And so it's a good idea to keep a label with your concentration so you know whether you're talking about the whole formula or just individual ions. And sometimes we'll look at specific ions. So I might, if I was looking at lithium phosphate here, I might say, what's the concentration of lithium ions? In which case I would multiply by a factor of 3 rather than 4 because I'm only interested in the lithium part. Okay, so let's take a look at percents. So this is something that I think your textbook kind of assumes you just sort of get intuitively, but just a few reminders here. Anytime we have a percent, we're talking about a part divided by a whole and then we multiply by 100%. So one of the things that is fairly common is to do a volume percent. So if you have rubbing alcohol, that usually is a mixture of water and isopropyl alcohol, and they'll say it's 70% or it's 90%. And that's just what volume of that is rubbing or is isopropyl alcohol compared to the total volume. You will also see things like a weight per volume percent. And so this is something that vinegar is using when you look at your vinegar concentrations in lab. Remember, you were kind of looking for about 5%, that 4 was the minimum, but usually it's around 5%. And a lot of times the bottle will tell you what the concentration is. So when you have that, what that means is you have 5 grams of the acetic acid, CH3COOH, divided by 100 milliliters of vinegar. All right, so this is 5 parts per 100 parts. And so we use 100 milliliters because water is about 1 gram per 1 milliliter. So that makes it work out. And then of course you multiply by the 100%. And we could do volume per volume. We could do weight per weight. A lot of the materials that we use when we make demonstrations, it's just a lot easier to say what the weight percent is. So the person who's preparing it just says, oh, I have to weigh out this many grams. They don't care how many moles is there because they're just making the same thing over and over. Okay, questions on this? All right, let's switch over to acids. Okay, so remember we talked about some acids are weak electrolytes. Some acids are actually strong electrolytes. They behave like ions or ionic compounds. And so when we're using this factor to determine when we're using this factor to determine our concentration, we need to know which one we're actually looking at. So you just have to memorize strong acids. Strong acids dissociate completely, I should say, in water. That's the solvent we're most commonly looking at. And so what this means is, if I take hydrochloric acid, there are no molecules of HCl in water. There's only chloride ions and hydronium ions. Just like if I have NaCl, there are no molecules of NaCl in there. There's only Na plus and Cl minus. There aren't very many of them, but they tend to be the ones that we use in lab. So 3 of them kind of go together. HCl is a very common one to use in lab. And then going down the halogen group, we have HBr and HI. And so the names of these all start with hydrochloric, hydrobromic, hydroiodic. And then a couple of weeks ago, you dissolved some copper using this acid. Anybody know what the name of that is? Nitric acid. And then at the beginning of the semester, when you were making your aspirin, you used this one as a catalyst. Uric acid. Very good. Now, these ones with oxygen are oxidizing, which means they can take electrons away from other materials, which is how the nitric acid dissolved the copper, took electrons away from it. Sulfuric is not as good of an oxidizer as the others. It's slightly oxidizing. But nitric is a very good oxidizer, so that's why we use that one. But an even stronger oxidizer is this last one, HClO4. And so since oxidation reduction reactions can be very exothermic, you may have noticed your beaker got warmer as you dissolved the copper. Having something that is extremely oxidizing can also lead to explosions. And so between that and the fact that it can dissolve flesh, we try not to put perchloric acid in your hands. And so we don't use this one too much. Now, all of these are going to have a factor of 2, because they're going to separate the hydrogen from the rest of the molecule. Except sulfuric's a little bit weird. Because it is diprotic. So that first hydrogen comes off very readily and acts just like all of the others. The second hydrogen acts like a weak base where it doesn't dissociate very much. So we kind of pretend like its factor is about 2, just like all of the others. But there's really some iffiness in there. So I will stick with these top 2 in my example problem. I will stick with HCl and HNO3 because those are the ones you use in lab. And you should absolutely, definitely 100% know their names, know their formulas, and know that they are strong. Okay. So in contrast, weak acids dissociate slightly. There might be a couple of exceptions, but almost all of them are less than 1%. So for every 100 molecules of HA, whatever A is, we've got one of the hydrogens coming off, and the rest of them stay together as HA. It is much more common for it to be even less than that. So some weak acids, it might be for every 10,000 molecules, we get one molecule of hydrogen. And so that doesn't affect the conductivity very much, and it doesn't affect our colligative properties very much. But because it affects them a little bit, we kind of avoid weak acids when dealing with colligative properties. They do affect them, it's just hard to capture. Okay, questions about acids? Okay, so for chapter 11, we're going to be looking at some new ways to calculate concentration. And one of them is molality. And so the names molality and molarity are very similar to one another. There's only one letter difference between the two of them. So you really have to be paying attention to notice that difference in a question. And sometimes it's really going to matter whether you're talking molality or molarity. So we've already talked about molarity as the capital M, and it's moles of solute per liters of solution. And when we say liters of solution, we mean everything that's there. When we talk about molality, we're still dealing with moles of solute on the top, but the bottom is kilograms, and it's just the solvent. It's not. We also use a lowercase m for molality and an uppercase m for molarity. So this is why in a lot of our formula, when we say moles, we just have an N instead of an M, because we got M's all over the place for other things. We don't want to confuse molality with just moles. So we might ask ourselves, why? So it's a lot easier to make something in lab by just measuring the volume. We don't really have balances that will let us measure large weights. In analytical balance, we can't measure anything over 100 grams. And even on the top loading ones, we probably can't get to a kilogram. We probably only get to half a kilogram. So if I wanted to make a large amount and I wanted to measure the kilograms, that would be really difficult to do. So molarity is just simple. So why not use it all the time? Well, one of the reasons has to do with temperature. So suppose I make my solution of sodium chloride that we had, 0.068 molar concentration, and I make it when it's 17 degrees in the lab, as it sometimes is in the middle of winter. But then next summer, I pull it out and the air conditioning stopped working and all the windows are open and it's 90 degrees. What might have changed?
Some of the solvent, or some of the solvent, like evaporated.
In theory, but we're going to say this was a closed container. All right, so I have in here these two things. They're called hand boilers. And there is a certain amount of liquid at the bottom. And so the tube isn't really, it's just very slightly filled because of capillary motion, but it's not very filled. But if I expand this liquid, then it might go up into this container. Here, let me do this in front here. All right, so you can see that as my hand is warming this up, that liquid is expanding, right? So much so that it's boiling now. Okay, so this happens, and it'll come back down for most things. Most things get bigger as we warm them up, and that's going to happen to the water in our solution. So that means that the moles per liter is going to be slightly different when it's 17 degrees than it is at 100 degrees. So when you use your volumetric flasks, they actually say on there, this is 200.00 milliliters at, and it's usually either 20 degrees Celsius or 25 degrees Celsius. Okay, so why? Because volume changes with temperature. So assuming we did have a cap on it, even if the volume is getting bigger or smaller, we're not adding more molecules of water. You're just moving it slightly away from each other. We're not adding or subtracting moles of solute. The number of particles is still there, and that's going to be the same, but the volume has changed. So for molality, does not depend on the temperature. Molarity depends on temperature. So this allows us to be a little bit more precise. And so because of that, most of the calculations, most of the formulas that we have for colligative properties rely on molality rather than molarity. For aqueous solutions, they're pretty close to one another because water has a density very close to 1. But if our solvent isn't water, that could be very different. So we just have to kind of pay attention to that. Okay, so let's look at some examples. We're going to take 2.5 grams of oxalic acid, and this has a formula of C2O4H2. And it's going to be dissolved in 9.1 grams benzoic acid. And so these are both organic acids. So organic acids have a lot more atoms in them. So we've got HCl is just 2, but oxalic acid, we have there 8, and benzoic acid, we end up having oh gosh, a whole bunch more. There's a benzene ring, so that's 6 carbons to begin with. So they're pretty heavy. And thus they form solids. Okay, so in order to find molality, we need moles of the solute. Which one is the solute? The oxalic acid or the benzoic acid? The oxalic acid, smaller amount, and plus we said it was dissolved in. So moles of oxalic acid, and that's going to be our 2.5 2.5 grams. And then we're going to have to use the molar mass. So we're going to look up our carbon on the periodic table. We're going to look up our oxygen on the periodic table, hydrogen. We're going to find that's 90.04. So where is the 90.04 going to go? The bottom, because that's grams per milliliter or per mole. And it follows that first unit of grams per 1 mole. Okay, so 2.5 divided by 90.04. Now, since I only have 2 sig figs, I probably could have just rounded to 90. And sometimes people will do that when you don't have anything that's very far off of the whole number. But I like to keep the 2 extra decimal places just so I don't use my molar mass to reduce my certainty. So this is 0.028 moles. And then I need kilograms of my solvent. This one's a little bit easier. Again, 9.1 grams. Kilo means 1,000. So I have 1,000 grams in 1 kilogram. And so move my decimal by 3. Okay, so my molality is equal to 0.028 moles of my solute divided by 0.0091 kilograms of my solvent. Which is equal to 3.1. Sometimes we'll just use the lowercase m for molal. Molal is the word for concentration. Or we might say 3.1 moles per kilogram. And we usually just say this is the molality of whatever the solute is. Sometimes if it's not aqueous, then we'll specify the solute. All right, so let's look at an example where we have 50 grams of ethanol. So I'm going to abbreviate ethanol as ETOH, but that has the formula CH3, CH2, so 2 carbons because it's F, and all means it's an alcohol, so we've got an OH there. And so this has a formula mass of 46.08 grams per mole. And I'm also going to have 50 grams of water. And we'll see in a little bit why, but I'm going to call water the solvent and ethanol the solute. Okay, so I want to know what is the molality. So my solute, I said, was the ethanol. So I'm going to take my 50 grams. And then I need to get to moles, so I'm going to use the molar mass. 46 is going to follow my first unit, which is the grams. So that's, I think that gives me 1 point. It's on the page. Okay, so what do I have to do with my solvent, my water? Yeah, that's gotta be in kilograms. So you might be able to do that in your head, but if you still need the help of unit analysis, 50 grams. We're gonna multiply it by a factor where grams is on the bottom, kilograms is on the top. 1 kilogram is 1,000 grams. We move our decimal by 3.050 kilograms of water. So our molality is equal to 1.1 mole divided by 0.050 kilograms. And so it's 0.15. That gives us 22. We might just use an M, 22 molal, or we might say 22 moles per kilogram. Okay. How many of you feel like you're kind of getting the hang of this? How many of you are completely lost? Okay. All right, I want to make sure that I go through examples of mole fraction before I do, so I'm going to do that because that is on the homework. So we talked about mole fraction before, but just briefly when we talk about gases. This is usually used when I can have any ratio of one thing to another thing. What do we call that when I mix two things and I can do it in any ratio? What are they? The vocabulary is miscible. And so it's especially used with gases. And so when we get to gases, there are a couple of ways we can arrive at this number, but I want to go with the logical way first, and then show you how you can get to the other one. So the mole fraction is really kind of like a percent. It is moles of A, whatever A happens to be, divided by total moles. Okay, so water and ethanol both have hydrogen bonding, so they're miscible. So we can think of that solution that we just had as being something we do with mole fractions. So we said 50 grams of ethanol gave us, what was it, 1.1 moles. And then we had 50 grams of water. So we're going to divide that by our 18.02. And that's going to give us 2.8 moles. So our total moles is 3.9 moles. So our mole fraction of ethanol, and this is why I said water was the solvent. Because even though they have the same mass, we actually have a lot more molecules of water than we had of the ethanol. So my mole fraction of 1.1 over 3.9, 1.1 is moles of my ethanol divided by 3.9 is my total moles. Gives me 0.28. And then I don't have units, okay, because I'm dividing moles by moles. So I usually just mole fraction of 0.28. For gases, moles, so remember N is moles, is proportional to pressure. Okay, so remember from PV equals nRT, if I increase the number of moles, I'm going to increase the pressure. Okay, and so I can talk about the partial pressure which is the part of the pressure of that gas that is attributed only to a particular chemical. So the whole atmosphere is 1 atmosphere, 764, but only part of that pressure is coming from oxygen, right? And so the way that I get there is by saying the partial pressure is equal to the mole fraction times the total. Total pressure. So that means if in a problem, like on your homework assignment, you're given partial pressures, because these two are related to one another, I can plug in the partial pressures the same way I would plug in the moles. So what is mole fraction? And knowing the symbols we use is important. So X or chi is our mole fraction. What is the mole fraction of, let's say, carbon dioxide if the partial pressure, so if I say PCO2, that means the partial pressure of carbon dioxide is equal to 3.5 atmospheres. And the total pressure is equal to 5 atmospheres. So I can say chi is equal to the partial pressure over the total pressure. The same way I would say moles over total moles. And so I would have 3.5 atmospheres divided by 5 atmospheres. I can't do that in my head. And again, no units because I'm dividing atmospheres by atmospheres. Okay. So those are the most common ways that we will look at concentration. I had a little bit of trouble with Chem Scale Builder because they kept wanting to use weird units that you don't see in your book and you don't see very often, called osmoles and equivalents and things like that. So I wish I had more practice problems I could set up. I may set up practice problems on Canvas for those of you that want to have more work with this. Chem 101 isn't very useful. All right, as you go home for spring break, make sure you are well rested before you drive long distances. No falling asleep at the wheel. All right, get lots of rest so that you're ready to go. Relax, have fun, turn off your brains for a while. Do some chemistry when you get back. Have a good break.